Good evening. Today I'll be presenting a summary of an important research paper by Ferreira and colleagues published in 2022, which introduces a new computational framework for analyzing composite laminates. The title of the paper is A Finite Element Unified Formulation for Composite Laminates in Bending Considering Progressive Damage. The work focuses on composite laminates, which are materials widely used in aerospace, automotive, and renewable energy industries. These materials are lightweight and very strong, but they are also complex to analyze because of their anisotropic nature. That means their stiffness and strength depend heavily on the direction of the fibers inside them. Now the paper introduces a new computational approach is better to understand how these laminates behave under bending loads, especially when they begin to fail. The key innovation lies in combining Carrera's unified formulation or CUF with continuum damage mechanics CDM. The combination was implemented in Abacus as a custom user element subroutine or UEL. In simpler terms, it's a specialized numerical tool that can model how cracks and damage progress within each ply of a laminate, while still being much faster and more efficient than traditional 3D solid laminate finite element models. To validate this method, the authors tested two kinds of cases. First, they analyzed benchmark problems such as laminated plates under sinusoidal and distributed loads. Secondly, they modeled a 3-point bending test of a composite coupon and compared the result with experimental data. In both cases, the CUF based approach was able to predict stresses, displacements, and the progression of damage with strong accuracy while also cutting down on computational time. The study also connects closely to how composites are manufactured. Typically, composites are made by stacking thin laminae layer by layer with fibers oriented in different directions to achieve desired properties. In the paper, the authors studied common stacking sequences like cross-ply, 0 by 90, symmetrical, and unidirectional laminates. They accounted for real-world factors such as residual stresses, defects, and ply interactions by homogenizing each lamina and using experimentally measured strength in both fiber and matrix directions. This makes their approach realistic and directly relevant to industrial applications. From a mechanics perspective, the paper touches both macromechanics and micromechanics. At the macromechanical level, each lamina is modeled as an orthotropic material with three main material directions. Using the constitutive equations of orthotropic elasticity, they captured the stress strain response under bending. At the micromechanical level, even though they did not perform detailed fibermetrics modeling, they relied on micromechanical principles to distinguish between fiber dominated and matrix dominated failure modes. This makes the model versatile and accurate without being overly complex. And finally, at the laminate level, the authors extended the classical laminate theory and shear deformation theories using cuff or CUF to capture non-linear stress distributions through the thickness. This allowed them to simulate how stacking sequences such as 0 by 90 by 90 0 or 0 10 respond to bending, and how damage progresses within those configurations. To conclude, this paper bridges the gap between theoretical composite mechanics and material structural simulations by combining CUF and with CDM. Ferreira and colleagues provide engineers with a computational tool that is not only accurate but also efficient. This makes it highly valuable for designing safe and reliable composite structures in fields where performance is critical, such as aerospace, automotive, and renewable energy. Thank you.